take a break. Okay, maybe we can start then. Let me enlarge the screen. Okay, last week we gave some information about asymptotic techniques and ray optics. To motivate the content of this lesson, let me start mentioning what are integral representation of wave fields. A wave, a general wave, in particular an electromagnetic wave, very often can be expressed by means of integrals. This is, for example, the case for a standard radiation integral in free space, but also in a bounded environment, actually, in which you express the wave, for example, the electromagnetic wave, in terms of the so-called primary sources. And the way to express the field in terms of the primary sources is to write down a superposition integral by exploiting the linearity of the medium, for example, free space, which is a linear medium. And the kernel of this integral representation is by definition the so-called Green's function of the problem. For example, free space Green's function, which is available in analytical form. Or if you are, for example, inside a rectangular three-dimensional box with perfectly conducting walls, then also in that case you can write the Green's function. However, in that case, that would not be as simple as in the free space case. For example, it could be given in terms of infinite series of modal fields, and so on. In planar stratified media, Green's functions are available in terms of Fourier integrals, and there are many other examples. There is also the possibility that the field is represented in terms of secondary sources. This is typical in diffraction problems or in scattering problems, in which typically the field is expressed in terms of some surface integral, where the integration is along some surface where the field is known either exactly or approximately. And we basically make use of what is known as the Huygens principle. If we know the field, for example, on the aperture in an opaque screen, then we may be able to find the scattered or transmitted field everywhere beyond the screen in terms of a superposition integral, again, in which the Green's functions are the kernels. Now, these radiation integrals or diffraction integrals, they can be evaluated analytically sometimes, but this is true only in a very limited number of cases. Typically, they must be evaluated numerically, and that's a whole area of applied electromagnetics, or they can be approximated through asymptotic expansions. This is the aspect that we will address in this lesson and in the next one. So here we will start giving some basic information about the techniques that can be used for evaluating asymptotically the integrals that can be used to express fields, wave fields in general. And the first kind of integrals we will consider is an important class of integrals known as Laplace type integrals. The name, which gives the name of this class of integrals, comes from the standard Laplace transform. As you know, Laplace transform is an integral transformation that takes a real or complex function f of a real variable t, where t is defined on the positive real axis. And this function f is transformed into a complex function of a complex variable s through this integral, in which, as you can see, the kernel is an entire function because it's a simple exponential, e2 minus st. The integration being carried out over the entire real axis. We will actually consider some generalized form of this kind of integral. And the generalization consists in the fact that the integration limits can be arbitrary real numbers, a and b, so not necessarily 0 and infinite. And furthermore, in the exponent of the exponential function, we will allow a general function of the integration variable t. We will call it phi of t. And this parameter k is the so-called large parameter, because we wish to evaluate this expression in the asymptotic limit when k becomes large. Note that there are two functions involved, the function f that multiplies the exponential and the function phi, which is in the exponent of the exponential. Both must be sufficiently smooth. We will be more precise later. Whereas k, the large parameter, is for the moment a real positive parameter that we will make tend to infinity, to plus infinity. This integral is, of course, a function of k. So the left-hand side is indicated as a function I of the large parameter k. Let us give the first example, which is the Laplace integral, the standard Laplace integral with finite integration limits. And let us observe that as the parameter k becomes large, so as k tends to infinity, the integrand becomes exponentially small because of the exponential function that tends to 0 for all values of t, with the exception of t equals 0, of course, because when t is equal to 0, the exponential function is equal to 1 regardless of the value of the parameter k. So in the neighborhood of the origin, we may expect that even though k tends to infinity, if we let t tend to 0, the product of k and t could remain finite. So we would expect, and this is the key observation for the evaluation of Laplace type integrals, that the global asymptotic behavior of this kind of integral, so its behavior for large values of the parameter k, is related only to the local behavior of the integrand in the neighborhood of the origin. So we may discard everything of the integrand and consider only a neighborhood of the origin. Just to give you a simple analytical example, take the integral j of the parameter k, defined as the integral from 0 to infinity of the product of a polynomial, first order polynomial, 1 plus t, times the Laplace exponential, e to minus kt. This kind of integral can be evaluated exactly, integrating by parts, and the exact result is 1 over k plus 1 over k squared. Now, if instead of evaluating exactly the integral, we limit ourselves to replace the quantity in brackets with its asymptotic value in the neighborhood of the origin, when t tends to 0, this bracket tends to the constant 1. So we replace the integral with a general integral, where integration is now performed from the origin to an arbitrary r value, capital R value, of the constant 1 times the Laplace exponential. Now, this kind of modified integral, in which we have taken into account only a neighborhood of the origin, both in approximating the quantity in brackets and in replacing the upper limit of integration with some arbitrary number r, can also be evaluated exactly. And the result is 1 minus e2 minus kr over k. This quantity is manifestly asymptotic equivalent to 1 over k, because the exponential is negligible. That's a term that is 0 beyond all orders. So if you compare the exact result above and this approximate result, you see that the dominant asymptotics is correctly represented, even though we have introduced approximations in the integrals. Okay. Now, this is the general philosophy. So what we expect is that the asymptotic behavior of this kind of generalized Laplace integral is determined essentially by the local behavior of the integrand in the neighborhood of the point, let's call this point C, where the function phi in the exponent has its minimum in the interval that goes from A to B, because that point will give you the largest value of the exponential function. Sorry. Note that we are focusing on the minimum because of the, okay, so the minimum of phi will give you the largest value of the exponential function. And in particular, we must distinguish two possibilities, because this minimum can occur either at the boundaries of the left, in which the minimum is at the left boundary of the interval, so when t is equal to a, or if the function is not monotonic, that could occur inside, so in some interior point between a and b, and that's the case depicted on the right, in the right figure. So we will separately consider those two cases. The first one is that the case in which phi is a monotonic function, and so the dominant asymptotics comes from the boundaries, either the left or the right boundary, depending on the shape of the function phi. And the second case is that in which phi has a local minimum inside the interval from a to b. Then let us start with the first case, the case of a monotonic function phi. And the simplest possibility is that the function f that multiplies the Laplace exponential is a regular function. So it's a smooth, sufficiently smooth that you can perform integration by parts. As we saw last week, integration by parts is perhaps the simplest of the asymptotic techniques. Take, for example, this integral, I of k, which is an integral along the positive real axis of this rational function 1 over 1 plus t squared to the second power that multiplies the Laplace exponential e2 minus kt. If we perform an integration by parts, we obtain this finite term that must be evaluated at 0 and at infinity, in which the rational function is the same as in the original integral, whereas the exponential has given rise to this ratio between the exponential and minus k. And now this finite part, when you evaluate it at infinity, is equal to 0 because of the exponential that wins against any rational function. What survives is the value at the origin, that is 1 over k. The remaining part is given by the factor 1 over k that pops out the integral, and then there is another integral, more or less of the same kind, a different kind of rational function, of course, times the Laplace exponential, so the process. And if you repeat it, you will discover that this latter integral will also give rise to a factor 1 over k plus something else. And so basically, the remainder can be evaluated as a big O of 1 over k squared. I hope you can hear me correctly, because sometimes I think that the microphone is not working properly. This kind of approach can be made rigorous. The rigorous result is as follows. If you have a monotonic phi and a regular function f, then by integrating by parts, what you obtain is that if your function f has n plus 1 continuous derivatives, while the derivative of order n plus 2 is piecewise continuous on the interval from a to b, then if you integrate by parts, you get a finite summation where small n goes from 0 to capital N, and all those terms come from the finite terms in the integration by parts, and in particular, the term of order 0 contains the value of the function f at the left-hand point, a. The next term contains the value of the first derivative at the same endpoint, and so on. All those derivatives are coefficients that multiply the Laplace exponential, again evaluated at the left-hand point. So as you can see, the left-hand point determines everything. And then there is this denominator, which is the n plus 1 power of the large parameter k. So we have an asymptotic series in terms of inverse powers of the large parameter k, where the coefficients depend on the behavior of the integrand at the left-hand point. In at least two directions. First of all, we can allow the upper integration limit to be infinite. and the result would remain valid. However, we must require that the upper integration limit, which is now infinity, does not cause any trouble. For example, we may require that our function f is of the order of some exponential e to alpha t, where alpha is some real constant, so that the integrand can be integrated in the neighborhood of infinity, at least for sufficiently large values of k. Because if your function f grows exponentially with the exponent dominated by the constant alpha, then as long as k is larger than alpha, the product of f times the Laplace exponential infinity, so you can integrate up to infinity. Okay. This is the first generalization. The second generalization is that we can also treat the case in which, instead of having t function of t, so a general phi of t, in that case the integral would be, as you can see at the bottom left, right of this slide, because even if you have this kind of generalized Laplace integral, then by simple change of variables, so by introducing the new variable tau, which is equal to phi of t, since phi is by assumption monotonic, you can change variables without problems, and you can reduce your integral to the case of a standard Laplace integral, and then use the result that is stated in this theorem. Okay. Now, there are occasions in which this procedure is that f can be not sufficiently smooth at the dominant endpoint, in this case the left endpoint. This integral, the integral from 0 to 5, which is of course a completely arbitrary upper integration limit, it does not matter, of this function to times the Laplace exponential. Now, if you try to integrate by parts, you will discover that you cannot evaluate the finite term. The term that multiplies the exponential is infinite there, because we have a negative power of t squared plus 2t. So you cannot do this. Now, what can we do in this case? Now, since repeatedly, this integral that we have given, in which the upper integration limit is equal to 5, should be asymptotically equivalent to the same integral in which the upper integration limit is replaced by an arbitrary number. That is because if we change the upper integration limit, we are introducing some exponentially small error that can be neglected with respect to any power asymptotics. So it is convenient to modify the upper integration limit and to let this capital R be some number less than 2. Why less than 2? In this case, we can expand the function that causes problems. So the function t squared plus 2t up to the power minus 1/2 by means of a Taylor series that converges only when t is less than 2. So this is why we are interested in this kind of boundary, upper boundary. In order to do that, we factor out the term 2t to minus 1/2. And what remains here is the standard square root, the reciprocal actually of something, where this something is less than 1. So we can expand this in a Taylor series, and by retaining only the linear terms, the terms up to the linear 1, what we get is 1 minus t over 4. If we now again distribute this factor here, we have 2t to minus 1/2 minus 2t to 1/2 over 8. So we have reduced our asymptotic evaluation to the evaluation of these two integrals corresponding to these two attempts. Now, the evaluation of these two integrals can be to the definition of a gamma function. What we need in order to obtain a link with the gamma function is to change again the upper integration limit and let it go to infinity in this case, because again, by changing the upper integration limit, we are introducing only exponentially small errors, so we can do that. But if we now do that, forming a simple change of variables, we can reduce those two integrals to the standard form that defines gamma functions. The definition of the gamma function is reported here at the bottom. That's an integral where the real part of the complex variable z is positive, of the product of a power of the integration variable t, where the exponent is z minus 1, and the exponential e2 minus t. So you can recognize that, for example, this first integral here gives the value of the gamma function evaluated when the argument is equal to 1/2, whereas the second integral is the gamma function evaluated for an argument equal to 3/2, or 3/2. So what you can see here in blue is the exact evaluation of those integrals, which will give you the dominant asymptotics of the function at the left-hand side. Okay. This example gives you the general picture. So what we did is to adjust the upper integration limit to our needs, to expand the integrand with the Taylor series, okay, integrate term by term, and then make use of the definition of the gamma function, again by adjusting the upper integration limit. If you do that, you have more or less proved a fundamental result in asymptotic theory, which is known as Watson's lemma, from the name of a great British mathematician that worked between the end of the 19th and the beginning of the 20th century. Now, this Watson's lemma says that if you have an integral function f, integrable in a neighborhood of the origin, so between 0 and some number b, and if this function behaves well in a neighborhood of infinity, so it grows not faster than some exponential function, e to ct, say. And now, if instead this function in a neighborhood of the origin admits an asymptotic expansion in terms of powers of the variable t, where the exponents are written in the form lambda n minus 1, and there are those coefficients, n goes from 0 to infinity, so this is a complete asymptotic expansion of the function f in a neighborhood, or better, in a right neighborhood of the origin, because in a Laplace integral we only deal with the positive side of the neighborhood of the origin, where those lambda values monotonically increase in order. So we have that lambda 0 is strictly positive and is strictly less than lambda 1, which is strictly less than lambda 2, and so on. Then under these conditions, the Laplace type integral I of k can be approximated asymptotically in terms of an infinite asymptotic expansion in inverse powers of k, where the exponents of k are given by the lambda n numbers. The a sub n coefficients are still there, but in addition we have the gamma function evaluated at lambda n. Okay, this is a fundamental asymptotic result, and actually this also when your parameter k is not simply a large real number, but a complex number. So you can replace k with this complex variable z, in which the absolute value of the complex variable z tends to infinity. So we have now an asymptotics in the complex plane, where we are interested in the neighborhood of the point at infinity of the complex. Usually holds in some restricted range of values for the argument. In this case, it can be shown that the formula provided by Watson's lemma holds if the argument of z is less than or equal to pi over 2 minus delta, that is, of some number which is strictly less than pi over 2. So you can imagine some angular sector which is contained strictly in the right half plane of the complex z plane. Inside this angular sector, this asymptotic formula holds, in which now the function I of the complex variable z is approximated in terms of inverse powers of z. Okay. Note that lambda n are numbers that are generally real numbers, not necessarily integers. Okay. Now, let us examine the second case, the case in which phi is not monotonic. And for simplicity, let us examine the simplest situation, that is the situation in which phi has a single point in the interior of the interval from a to b, where it has a minimum, so where its first derivative is equal to 0, and the second derivative is positive, strictly positive. So we are now considering a point C that is strictly between A and B. We will also assume that this is the only point where the first derivative is equal to 0 inside the entire integral, the entire interval. And furthermore, that the functions f and phi are sufficiently smooth in order to be able to perform all the manipulations that we will do. Now, again, we will expand both functions in the neighborhood of C, which is the point from which we expect the dominant asymptotics comes. So, first of all, we integrate C, so from C to minus R to C plus R, where R is somewhat arbitrary. Then we replace the function f with the constant f of C, so the value of the function evaluated at the point C. This is a strong simplification. And furthermore, we approximate the function phi in the exponent through its Taylor expansion truncated to the second order, which is the first non-zero order beyond the constant term phi of c, because our function phi, by assumption, has its first derivative that is equal to 0 at the point c. So the next term from the constant 1 in the Taylor expansion is the second derivative evaluated at point c, divided by 2. Now, what can we do with this kind of integral? Well, first we have a simple Gaussian exponential in the new variable tau, and the variable tau is linearly related to the old variable t by this kind of coefficients, the second derivative of phi evaluated at c. So you will see that the integration limits must be changed because of this change of variables, and also there is this denominator here that comes from the Jacobian of the change of variables. Okay. The exponential evaluated at c has also been brought outside the integral. So as you can see in the numerator, we have the function f evaluated at c, and the generalized Laplace exponential also evaluated at c. And now the last step is that k is a large parameter, so it tends to infinity. The integration limits go to infinity, to plus and minus infinity, so they converge to the Gaussian integral. And this convergence is exponential, so you can replace these finite integration limits with the infinite ones without introducing appreciable errors. And so you can replace the entire integral with the value of the Gaussian integral, which is the square root of pi. So you find the final formula of the Laplace method, in which you can see that the asymptotics is given by the value of the integrand evaluated at c times this square root that contains a fraction with 2 pi in the numerator, and in the denominator you see the large parameter k times the value of the second derivative evaluated at c, which is an important And here you can see everything made more explicit and with some more rigorous statements about the degree of smoothness. You have a function phi whose first derivative vanishes in some interior point C and all same point. And if the first derivative does not vanish at any other point in the same interval, if your function phi is in C4 of inside this integral, so it has 4 continuous derivatives, whereas the function f is of class C2, just derivatives. If your point, as we assumed so far, what we get is the asymptotic formula that we have just proven. And furthermore, we have not shown the error, the asymptotic error that you commit is of the order e2 minus k times phi of c divided by k to 3/2. So the next asymptotic term is of this order, whereas if the points you have a 0 derivative at some endpoint, you get this factor, which is quite intuitive since we are only considering one left or right neighborhood of the point C, is this factor here. And in addition, it is shown that the error has a different asymptotic order, so it's not it does involve the inverse power of k over 3/2. It involves 1 over k, asymptotic decay in the error. Okay. Some remarks. The main idea in the rigorous proof of the Laplace method is to split the interval into half-open integrals, one on the left of the point C and the other on the right of the point C, in each of which the function f phi is monotonic. That is because we have assumed that the function phi has a single point in which its first derivative. So that if you change variables, then you can apply Watson's lemma. Take, for example, the right half interval that goes from C to B. In that case, if you change variables by means of this expression here, where the new variable tau is equal to phi evaluated at t minus phi evaluated at c, what you get is that, first of all, inside the integral, you have the standard Laplace exponential e2 minus k tau. Second, this exponential has popped out of the integral, so you have e2 minus k times phi evaluated at c. Then the integration limits have changed, but above all, you have the term phi prime of tau that comes from the Jacobian of the change of variables. Okay, so in this case, you have now in the condition of using Watson's lemma. And Watson's lemma can, in principle, provide you with infinite asymptotic expansions if you know the infinite asymptotic expansion of the integrand in the neighborhood of the left integration limit. By the way, the left integration limit, I guess, should be 0 in the second integral and not c. Yes, it is 0, so this is a typo. This is an important remark because Watson's lemma is able to provide infinite asymptotic expansion, and therefore also the Laplace method, which is based on Watson's lemma, can give in principle a complete asymptotic expansion. And we will make use of this fact in the next lesson when we will apply this to the so-called steepest descent method. Other remarks are that Laplace's method can also be used when the function f either vanishes algebraically or it becomes infinite algebraically. For example, imagine you have been given this kind of integral from 0 to 5 of the sine function of s times the exponential e2 minus k, the fourth power of the hyperbolic sine of s. Now, first of all, from an asymptotic point of view, you can replace the upper integration limit with an arbitrary number, r. And you can replace the sine function with its Taylor expansion. For example, the first term in the Taylor expansion of the sine function is the linear term. So you can replace the sine with its argument, s. And furthermore, you can do the same in the exponent of the exponential function. So you can replace the fourth power of the hyperbolic sine with the fourth power of s without changing asymptotically anything. Then we can change variables. So we let s squared be equal to t, and this gives you this second form of the integral. Well, now the upper integration limit is the square root of the previous one. And finally, we again change variables. So we introduce tau in order to have the standard evaluated to 1/2. So the final asymptotic form is this nice our integral k to minus 1/2. This is a first example. Another example is this in the bottom part of the slide, where you can see that the Gaussian exponential is divided by the square root of the hyperbolic sine of t, which is a function because the hyperbolic sine tends to 0, and so therefore, since it is in the denominator, this goes to infinity. However, again, we can replace the hyperbolic sine with its argument and perform the integrations analytically by introducing the gamma function, in this case evaluated at 1/4. Thus, we discover that in this case, the asymptotics is proportional to 1/k to 1/4. Okay. And another important example is the asymptotic expansion of the gamma function itself, whose definition is recalled here. In this case, we write the gamma function with the argument k plus 1, so that inside the integral we have t to the kth power times e to minus t. We are interested in evaluating these for large real values of the argument, so when k tends to infinity. One thing one could try to do is to represent the term t to the kth power as an exponential in order to recover the form of a generalized Laplace integral. So we could write e to k times the logarithm of t. So in this case, we would recognize as the function f the exponential e to minus t, and as the function phi the logarithm function. However, if we do so, we find a difficulty in that the maximum of the function phi occurs at infinity, where, however, the function f decays to 0, and it does so violently because it's an exponential decay. So the point where you would expect the dominant asymptotic comes is also a point where the integrand is negligible beyond all orders. So this isn't the right way to do. What we can do is instead to make those two terms in the integral a unique exponential, k times logarithm of t minus t, and try to find the maximum of this exponent by differentiating this with respect to t. If you do that, we will discover that the maximum occurs when t is equal to k. And so this is a movable maximum, because k is a parameter that is going to infinity. So infinity as you let k go to infinity. This is, of course, not convenient, but we can avoid this difficulty by a simple change of integration variable s by introducing by introducing the new integration variable s, which is t divided by k. So in this case, what we get is that the movable maximum at k becomes a fixed maximum at s equal to 1. Now, if you do that, the Jacobian of the transformation will give you this term here, k to the power k plus 1, of minus k times s minus logarithm of s, which is our new function phi. So we have reduced ourselves to this final form in which we have a generalized Laplace integral in which the function f is just constant equal, and the function phi is equal to s minus the logarithm of s. Now we can evaluate these. At this fixed maximum s, the function phi is equal to 1. The second derivative is equal to 1. The first derivative is, of course, 0, since this is a maximum. So we can now use the standard formula for evaluating Laplace integrals. And what we get is the term coming from the Jacob, then the integrand evaluated location of the maximum, that is when s is equal to 1, and this gives us a e2 minus k. And finally, this square root function that becomes here the square root of 2 pi divided by k. Or if you compact everything, you can write as in this red expression, the square root of 2 pi k times the kth power of k over e, which is known as the Stirling approximation or Stirling Laplace approximation of the gamma function, or equivalently of the factorial, because you may remind that the gamma function evaluated at the argument n plus 1, where now n is is an integer, is equal to the factorial of the number n. So we have the Stirling approximation of the factorial. Okay. Okay. Maybe it's a good idea anyway to make a 5 minutes break. So let's see at 10:50 for the second part of this lesson, which is instead about Fourier type integrals. So see you in 5 minutes or so. Okay, here I am back. Okay, we will now examine a second class of integrals known as Fourier type integrals. The name comes from the prototype, which is the standard Fourier transform. There is an integral along the entire real axis of the product of the function f and the exponential function, in which now you have an imaginary unit, the exponent j, times the variable omega and the integration variable t. We will generalize this standard Fourier transform by considering integrals along finite intervals, that is from a to b. And also we will allow the exponent of the exponential to contain a general function phi of the integration variable t, which is multiplied times a parameter that we will call k, which again will be a large real parameter. So we are interested in finding some asymptotic expansion of this integral seen as a function of the parameter k, so the function I of k in the limit where k goes to infinity. Now, a first value of any Fourier type integral tends to 0 under very general conditions. This is a consequence of the fact that as the parameter k tends to infinity, the exponential factor oscillates faster and faster. So these oscillations will cancel themselves. So the value of the integral is forced to vanish in the limit when k tends to infinity. This result is known as the Riemann-Lebesgue lemma. And technically, this says that the Fourier integral tends to 0 as k tends to infinity, provided that the integral of the absolute value of the function f exists. So this is an integral function within your integration limits. And also that the function phi in the exponent is a continuously differentiable function in the integration interval. And also that phi is not constant on any subinterval of the integration range. Okay. Having said that, the asymptotics of Fourier type integrals can be obtained by considering this basic intuitive remark. Suppose that you have an interior point C inside the integration range, for which the first derivative of the function phi in the exponent does not vanish. Now, if omega C is a small neighborhood of this point, then we could expect to approximate our generalized Fourier integral by approximating the function f with its value at the point C, and this means that this constant value f of C outside the integral, and then limit ourselves to integrating in this neighborhood omega exponent of t. Now, however, as it tends to infinity, this kind of Fourier rapidly, and this produces cancellations that tend to decrease the value of this kind of integral I sub c. However, if we instead assume the first derivative of phi t, then even if k is a very large number, there will always exist a small neighborhood of the point C throughout which the product of so rapidly. So in this region, the exponential oscillates less rapidly than anywhere else, and so less cancellation occurs. So this is the reason why we expect that the dominant asymptotics of a Fourier integral comes from the points where phi prime vanishes. And this gives the name to the method. Since in many applications the function phi has a physical interpretation of a phase, the method for asymptotically evaluated this kind of generalized Fourier integrals is known in physics as the method of stationary phase. And also, in this case, as for Laplace type integrals, we will need to consider separately two cases: the cases in which phi is monotonic, and therefore the focus will be on the boundaries of the integration range, and the case in which instead phi has a stationary point in the interior of the integration range. In the first case, integration by parses, when possible, is again the technique that provides you with the asymptotic expansion. So if you integrate by parts, what you get is what you can see in this box, in which we have assumed that our function f has n+1 continuous derivatives, whereas the next derivative of order n+2 is piecewise continuous inside the integration range with a finite integration range, so a and b are finite. Then under those assumptions, the integral can be asymptotically estimated by means of this finite summation, where small n goes from 0 to capital N, and in which what you see is the contribution of the endpoints that comes from integrating by parts. So you can see inside the square brackets, there is the difference of the values of the same thing evaluated at the right and at the left endpoint. You can see the values of the function f and of its derivatives up to the order capital N. And in front of the brackets, you can see this fraction in which you can see the powers, the progressive powers of the large parameter k. Also, in this case, this result can be generalized to allow the existence of a function phi in the exponent, which is monotonic, because also in this case, you can reduce to the standard Fourier integral by a simple change of variables. Okay, so this is the first asymptotic result. Just to give you an example, if you have the integral from 0 to 1 of the Fourier exponential divided by parts progressively, this is what you get. And this is an asymptotic expansion that can in principle be brought to any orders. Okay. For the cases when integration by parts fails, and this is the case of a singular function f, we have a sort of generalized Watson's lemma, in which if you have now a function f which is 0 with all its derivatives at the right hand point, so we need to exclude the right hand point from our considerations with this assumption, whereas f exists with all its derivatives in a right neighborhood of the origin, and furthermore the function f is asymptotic to the power t to gamma in the right neighborhood of the origin, then the Fourier integral can be evaluated as you can see in this rather complicated looking expression, in which you can see again there is an inverse power of k, the exponent being gamma plus 1, and then there are numerical constants, the gamma function evaluated at gamma plus 1, and this exponential function here. When phi is instead not monotonic, we will consider again the case of a single interior point where the first derivative vanishes, okay, as we did in dealing with Laplace integrals. Now again, as in that case, we can expand both functions f and phi in the neighborhood of this point. This produces an integral of this kind. The integration limits can be restricted to some neighborhood of the point c, so we go from c minus r to c plus r. The function f is replaced with its constant value at the point c, and in the exponent we again approximate the function phi through its Taylor series representation truncated to the second order, which parallels that of Laplace integrals. However, keep in mind that now the exponent is purely imaginary. Okay. So as we did with Laplace integrals, we now change variables by introducing this sine function mu, which is equal to plus or minus 1, according to the sign of the second derivative of the function phi evaluated at the point C, to change variables so that the new variable tau is equal to t minus c times the square root of the absolute value of the second derivative evaluated at c of the function phi times k divided by 2. If we do this rescaling of the integration variable, what we get is this new form of the integral in which some terms have been taken outside the integral, including this square root that contains the large parameter k. The large parameter k is also contained in the new integration limits. So when you let k go to infinity, those integration limits go to infinity, and this integral with infinite integration limits tends asymptotically exponentially to this constant of j by mu divided by 4. So all in, what we get is again a nice asymptotic formula, which is the dominant asymptotics of the generalized Fourier integral, that is given in terms of the integrand evaluated at the interior point C times this factor that is very similar to the same factor occurring for Laplace type integrals, but note that now we have an absolute value of the second derivative of the function phi. And finally, we have this exponential with a purely imaginary exponent in the last term. Okay. And this is the content of the stationary phase method, which is now stated again explicitly. So if you have a single point t equal to c inside the integration range where the function phi vanishes, if the function f vanishes infinitely smoothly at the two endpoints necessary if we want to neglect the contribution of those endpoints, and if both the function f and the function phi are infinitely differentiable on the two half-open intervals on the left and on the right of the point C, where they admit this kind of asymptotic behavior locally, so the function phi is close to phi at C according to this kind of behavior. So it's the second power of t minus c times some constant alpha, whereas the function f is asymptotic to t minus c to some exponent gamma, and there is also the coefficient beta. Note that gamma must be larger than -1 if you wish your function to be integrable. Then the asymptotics of this generalized Fourier integral is given by this formula here that generalizes the previous one, where again we have the Fourier exponential evaluated at c. Then there are some constants, beta, the gamma function, this exponential here. And finally, the large parameter is contained inside this algebraic term here, in which you can see k is in the denominator, and it's elevated to the power gamma plus 1 over 2. Okay, this is the dominant asymptotics. The error is of the order k2 minus gamma plus 1 over 2. So that is, it's of order smaller than this because it's a small o. Okay, and again, mu is the sign of alpha. This result, the stationary phase method, can also be generalized in different directions. For example, you may allow the function phi and also the function f to have different asymptotic behaviors as you approach the point C from the right and from the left. Here there should be a minus sign in the superscript of the. For example, if you have behavior that involves alpha plus and beta plus as coefficients, and ni and gamma as exponents, respectively for phi and for f. Then the contribution to the Fourier integral of the right part of the integration range, so when you integrate from C to B, is given by this kind of generalized formula, similar to the previous one, but now involving both the exponents ni and gamma, in instance alpha plus and beta plus. And something similar could of course be written also for the remaining integral, the one that comes from the left side of the point C. To give you a final example, let us evaluate the leading behavior of the Bessel function of the first kind, J sub n, evaluated for the argument equal to its order. So we have n also as the argument of Bessel function in the asymptotic limit when n goes to infinity. To evaluate asymptotically the Bessel function, we will start from one of the many representations that exist of Bessel functions. In particular, we will use an integral representation, which is represented as 1 over pi times 2 pi of the cosine function, having as argument n times the sine of t minus nt, where t is the integration variable, written as the real part of an exponential e to j n times sine t minus t. So we have a standard Fourier integral in which n is the large parameter and the function phi is the sine of t minus t, which is asymptotic to, by means of a Taylor expansion, t minus t to the third power divided by 6 plus higher order terms. Now, if we truncate the Taylor expansion of the sine up to this order, we can evaluate the blue phi function as approximately as divided by 6. And so we are now in the position given for standard Fourier integrals, in which now the point C is at the left-hand point 0. So we evaluate only the contribution from the right neighborhood of the point 0. And this is the result, in which you can see the large parameter is here elevated to the power 1 over 3. This 3, of course, comes from the asymptotic behavior of the function phi in the neighborhood of the origin. Since it behaves like the third power of t in the neighborhood of the origin, this translates into the asymptotic behavior n to 1 over 3. Okay, I think that we are almost done. I will give you a final remark. If you compare the Fourier and Laplace type integrals, you will see that for Fourier type integrals, for example, although the stationary points give the dominant contribution to the asymptotics, if you need to go beyond the dominant asymptotics, then you should also consider the endpoints, because those provide you terms that are smaller than the dominant one. However, they are only algebraically smaller than the dominant one, to the higher order asymptotic terms in an infinite asymptotic expansion. In contrast, for Laplace type integrals, the entire asymptotic expansion depends only on the behavior of the integrand in a small neighborhood of the global minimum of the function phi that occurs in the exponential. That is because that's a real exponential. So the points away from the minimum are exponentially small in comparison. So you never deal with endpoints when you have Laplace type integrals. That is basically the mechanism of cancellation that underlies the asymptotic expansion of Fourier integral type of decay mechanism than the one provided by the real exponential that occurs in Laplace type integrals, that is able, via Watson's lemma, to provide you the entire asymptotic expansion of the Laplace type integral. And that's all for today. What I say today is taken from the book by Ablowitz and Focus, in which you will find many other examples, and you can go deeper in these subjects. Next time, we will address a single specific asymptotic technique, which is probably the most important in practice. That is the so-called steepest descent method. We will see that this is a generalization in the complex plane of the Laplace method we have discussed today. So thank you again for your attention. For today, it's all. And let's see on Thursday.
I'm sorry. Could you send today's slides by email? Because I have some issues with the e-learning.
So you did not manage to enter. Okay.
Okay. No.
Okay. Do you need only those of today? So
also the last lesson.
Okay.
Okay.
Okay. Thank you.
I also have the same problem. So please, if you could also send them to me.
Sure. Okay. I'm wondering why this occurs, because I enable guests and it seemed that it worked in the first days of the course, right? So you managed to enter
in the first
at the
days,
beginning.
yes.
Now I don't know
Yeah,
what's happening. Okay, I will try to find it out. In any case, I will send you the PDFs also by email.
Okay, thank you very much.
Thank you.
No, you're welcome.
Thank you, Professor.
Have a nice day.
You too. Bye bye.
Ciao.
Bye bye.
Grazie mille, buona giornata.